Hi, I'm Owen, and I'm here to talk about um, a AIIDE, or Artificial Intelligence and Interactive Digital Entertainment 2022 conference poster paper, a review of uncertainty for deep reinforcement learning. Unfortunately, I will not be at the conference in person to talk about this work. Um, I wrote this when I was still at university, and I've since graduated. So acquiring funding is not very easy or not very feasible for this sort of situation. Um, I am hopeful that I will be able to uh, answer any questions that people might have in the video. And if you have any more questions, of course, you're welcome to email me or leave questions in the comments. Um, this was a really enjoyable work to write and to research and all of that. It was my first review style paper, so it was a great experience there. It's very different, than what you usually think of. I think I still have a lot to learn when it comes to writing great review papers. It was also good. I know there's a lot of issues with peer review these days, but I think the peer review was pretty good that this went through. So all around, I'm excited to talk about this. My co-author there will be in person to present this. Um, and so without any further ado, let's get right into it. So um, you may also notice that I'm presenting in this weird mode. I'm not using the full screen mode because I just downloaded this LibreOffice because it is free. And my university account of Microsoft PowerPoint and Office and all that stuff recently expired, unfortunately. Just like funding for that is also run dry, I guess. And so I've used LibreOffice as a free alternative before, but I'm not familiar with how to work with it in terms of my recording software and everything like that. So I figured, just get this done and um, we'll make do with the way it looks currently. I think this is I think it should be pretty good. It takes up most of the screen. Yeah, so without any further ado, let's get into this. So I'm just going to explicitly address the target audience and sort of goals of this presentation right now. So the audience, right, is for people looking to do something cool with RL, basically. Um, we'll get to this in a little bit, but there's a lot of problems with RL, especially applying it to any sort of reliable situation. You can use it to, beat chess players or beat StarCraft players, but even in that, there's some brittleness. So people who are looking to make RL work in their situation, and people looking to make more robust RL algorithms. For people already extensively familiar with uncertainty in RL, or even extensively familiar with the literature of RL, you'll probably know a lot of what's being said. So that's just why I leave the target audience as such. The goals is basically just to introduce some of these uncertainty concepts, really basic introduction, and just highlight some existing works and show, there is value here. And basically, all I'm trying to say here is to encourage people in the applied RL setting or in the robust RL setting to try and look more into explicit uncertainty quantification and see if it can help or work with your scenario. That's really all I'm trying to get to here, is just to say, here's this cool stuff that a lot of people have done. Here's how it can work, and maybe it can work for you. And that's really all I'm trying to do here. So let's get into it. Reinforcement learning and games have obviously had a strong partnership for a long time, especially deep reinforcement learning. We can see here a number of papers. I realize it's very biased towards certain companies in the representation here, but that's simply because I was looking for pictures, and the Nature cover papers have nice pictures. So we can see Atari, Go, Shogi, chess, um, StarCraft 2, Dota 2, all of these have sort of been uh, influenced, and I don't want to say mastered in a sense, because not all of them have been mastered, but successful to reach the state-of-the-art performance, shall I say, and reinforcement learning has enabled a lot of this work. However, it's often struggled when you try to integrate it into these games. So, and for game designers to use RL for enemies or for NPCs or for, you know, cars driving around or something, there's been a lot of challenges. And so we'll get into that on the next slide. And here I, rather than writing my own slide, I stole someone else's here. You can see the Twitter link where I took this from. But there's a lot of problems, definitely, with integrating RL into games. And this isn't, I'm just using games here as a focus because, you know, we like to talk a lot about games at AIIDE. But this is true of any sort of application centric RL, is that there's challenges in getting it to successfully integrate. Now, uncertainty quantification won't address the funness, perhaps, or the quirkiness, but there is potential for accelerating the time and the resource intensity and the brittleness. There's a lot of potential here, and I'm not going to make any outrageous claims saying, you know, one simple trick of uncertainty quantification will solve everything, but seeing AI's interaction with seeing sort of out of distribution data is something that's a very big incentive for uncertainty quantification, because you can sort of be aware of that at the very least. You can know what will probably break your AI, even if you're not able to fix it. And so, right, because if it's going to have a lot of uncertainty when it's never seen something before. And so, yeah, this is, I think, just goes into the motivation of saying, you know, uncertainty can help in a lot of situations, and there's a lot more work to be done here too. So I'm just trying to incentivize people to explore this area as well. So just getting into sort of the basics, right? Reinforcement learning, what is RL? If you've never heard of it before, it's basically just a field of machine learning that seeks to maximize numerical reward signals based on environment interactions. We can sort of separate this into two types of RL, online and offline RL. Online RL is sort of what you typically think of when it comes to this, where you have your little agent and it's interacting with its environment, you know, in a very standard way, and it's learning based off of those interactions. Offline RL is a somewhat new conceptualization in the deep RL field, and basically you're given a data set of interactions. So in online RL, those interactions are based on what your agent's actions are. But in offline RL, those can be random or based on a median, you know, human performance or something like that. And so you have to either use just those actions or just those actions in a tiny bit of online training. And this is difficult. It sounds at first just like a supervised learning problem, but there's a lot of challenges there, that you're not just necessarily trying to clone the behavior because you might be given bad interactions. I mean, obviously you want to clone perfect behavior, but very rarely do we have access to perfect interactions. And so this has been shown to have more difficulties, and more, maybe a better phrase would be different difficulties than just supervised learning on a data set. So not a lot of math in this presentation. This should be the only formulas you're going to see here. I'm trying to stay very high level. But in deep reinforcement learning, there's two main, well, there's really three, but we'll focus on two main branches here of algorithms. We have these value-based methods, such as the deep Q networks, which try to directly learn and act via predicted values of state. So for example, the Q value, which is the value of the state action pair, it tries to learn all the Q values for a given state, and then pick the one with the highest value, because that should return the highest reward. And so that was very common, especially early on. That was like the 2015 or 16 Nature paper that DeepMind did with Atari. That was a double DQN. But it's not as common anymore for large scale systems. For example, Dota 2 was a actor-critic proximal policy optimization. StarCraft 2 was a unique algorithm. That doesn't fit neatly into an existing name. And GT Sophie, which was the new Sony AI for their Gran Turismo racing game, was a soft actor critic algorithm. So PPO and soft actor critic are obviously actor critic methods, which basically learn a value function of some kind. And so this can be the advantage, this can be the Q value, this can be the state value. There's a lot of things that this can be, and use it to inform the updates of this policy. And this is, if there's any mathematicians out here, this is not the mathematically correct formula. You have this gradient sign, gradient with respect to what, but this is sort of just the idea is that you have this gradient of this objective that you're updating, and it's based on your policy pi and some value, and that's what the sigma represents, or sorry, delta. That's what the delta represents. It's just some value. That could be the advantage, that could be the Q value, and so that's what's being represented here. It's just saying that, look, the updates depend on both the policy and the advantage or value, whatever is being learned there. And you can see, if I go back to the Q function definition, you can see pi there's the policy, and we're maximizing the reward, the expected reward over this time, according to that, where you pick your actions based on that policy. And so pretty much everything past like 2013 uses deep neural networks to represent these functions. So the Q function is a deep neural network. The advantage function is represented in a way from a deep neural network. The policy is a deep neural network. Everything's deep neural networks. And so that introduces a lot of benefits that we have clearly seen, but there's a lot of tricky things when working with deep learning. So moving on, this is far from a comprehensive overview of deep RL, but just some light introductions and some key ideas that we'll see, especially this equation for actor critic. You'll see that in the discussion. So now let's talk about uncertainty. What is uncertainty? Well, we all know what the word literally means, but we're going to be talking about a helpful heuristic here, and that's breaking down uncertainty into sources or kinds of uncertainty. So we have epistemic and aleatoric uncertainty. So we can think of, our model is uncertain about, or I shouldn't say our model, our agent is uncertain. The environment is uncertain. There's, uncertainty everywhere. How do we break this down? In the case of epistemic uncertainty, we have uncertainty originating from the model. So basically, you have a brand new model, right? No training done. It's going to be really uncertain. It's literally never seen anything. It can't predict, like its predictions are random, effectively, assuming you randomly initialized it. There's no, certainty in its predictions. And so this type of uncertainty, one of the key aspects of it is it's reducible. So you can reduce the training or the uncertainty there by simply training the model. There's also aleatoric uncertainty, and this is uncertainty that originates from the problem or the environment or whatever we're looking at. And you can't reduce this. It's there, right? If I'm flipping a coin, you never know what it's going to predict. Like, that's an irreducible uncertainty, no matter how much you know. Although I guess if there's some determinism in the coin flip, then maybe you could predict it. But basically, that's the irreducible noise in the environment. And so in supervised learning, we often model the noise as we have these noisy labels that are some true labels plus our noise model. And you'll see this going way back to linear regression, right, where you model this noise as a Gaussian, and you can do all sorts of things with that. However, it's very context dependent. See this figure taken from reference 3, which will be at the end of this presentation, where we can see on the left, we have data with some irreducible uncertainty. It's one-dimensional. So there's an x1 coordinate, and it's a binary data set. Well, in the middle there, for example, x equals 0, let's just say is the middle right here. you don't know what it's going to be. There's no way of separating them, because remember, this is our only feature. There's no way, right? You can't separate them. And so that's irreducible noise that prevents you from linearly separating this data set. But let's project it into a higher dimensional space in which it's now linearly separable. In this space shown on the right, where we just added a feature, we can see that we reduce the aleatoric uncertainty by doing something. We, modified the parameters of our problem, so to speak. But I just told you aleatoric uncertainty can't be reduced. So what's going on here? And this shows how it's really context dependent, and it's not perfect either. I encourage you to read the reference 3 paper, if you're interested in more information on this. But really what I'm getting at here is that this uncertainty is very problem dependent, and it's a heuristic for understanding this. It's not the end all be all definition. All right, now let's talk about uncertainty and aleatoric uncertainty and reinforcement learning. So I'm going to highlight 3 potential sources here where you can have uncertainty in this environment, right? Because this is irreducible. So we're thinking outside the agent. This is uncertainty that cannot be reduced through learning with the agent. So it comes from the environment. So we can have, if you think about the sort of typical MDP, we can have our rewards. Our reward function could be non-deterministic. I didn't think of a good example right here that a real game would have. I know there are games, I just couldn't think of any off the top of my head. So I put in Calvin Ball, which is a classic game from Calvin and Hobbes, where the rules are very flexible and the scoring is very flexible. And so it's definitely non-deterministic. Non-deterministic observations, right? If you're saying, okay, I see my current setup, but I don't know what's going to happen next. StarCraft 2, I don't know. Something's going to come out of the fog of war, I don't know. Poker, what's the next card? I don't know, right? There's uncertainty there that you can't do anything about. Now we're going to talk about modeling in a second, but for now we're just going to leave it at that. And then there's non-deterministic actions, where, for example, if you have some stochastic algorithm, for example, PPO, soft actor critic, where you're saying, okay, I'm drawing my action from a distribution. Well, then you don't know what your action is going to be. You can model it. You can say, okay, I know it's going to be drawn from this Gaussian distribution, but I don't know what the exact value is going to be. And so that's sort of an agent based uncertainty. But anyway, the important point I want to throw out here and discuss is actually something that this nuance especially was emphasized by one of the reviewers. So I want to thank the reviewers for their work in this project. And that's distinguishing between modelable and non-modelable. So, for example, in poker, I can know exactly, and good poker players do know exactly what the odds are of any given hand or of any given card being drawn next. So you can say, okay, the next card that they're going to flip over, is going to be a 2 of spades with, a certain number of odds, or it's going to be, you can do the odds for every possible card, but you can't actually know. So it's irreducible, right? You're not going to know what the next card is, but you can model it and you can know what it could be with the exact odds. Whereas StarCraft 2, you can't model it exactly. You can say, you can make informed heuristics like, okay, I saw my opponent building a ton of barracks early on. Maybe there's going to be a lot of Marines about to come out of fog of war, but that's not an exact model or a meaningful statistical model. And so that's a big difference that I want to highlight here, is that in both cases, aleatoric uncertainty is irreducible. You can't know more, but it can be useful to still model it. For example, if we said, we don't know what card's coming next, who cares? I'm just going to ignore that completely. That would be a terrible poker strategy. And a little bit of this that I just talked about here sort of highlights the difference between Markov decision processes and partially observable Markov decision processes, in the sense that the state of poker can be thought of as fully observable. At least in your hand, right? You see all data on your hand, whereas in StarCraft 2 you see only, part of the map. Now obviously, okay, you don't see other people's hands in poker, so maybe that's not the best, example. But in StarCraft 2 you can definitely not see or know the underlying model. So you don't know what's going to happen next, and you have incomplete observations of the true state, right? If the true state is every pixel on the screen, you don't see every pixel. So that's not always the most apt difference, but that is an example there that I'm just drawing a parallel to. So now with epistemic uncertainty, there's been a lot of research in the classical sort of deep learning for supervised learning world that I'm not going to touch on, but there's a lot of work out there, lots of it, that I recommend you can investigate. But very little has actually been translated into reinforcement learning. So I think there's a lot of room there specifically for this work to be translated over. But the important thing that I want to note here is that epistemic uncertainty can be reduced. However, there's non-trivial challenges in RL. So for example, if you're saying, okay, I want to reduce my epistemic uncertainty, let's throw more representative data at it, just reduce it by training it. But we can see in RL that in supervised learning, right, if we just train forever, assuming our model has sufficient capacity, we can usually get things to overfit, basically, where we do really well on, some subset performance. But in RL, we often see, or we can see that if you train forever and ever and ever, right, people see this on trivial experiments with DQN for cart pull, that you see catastrophic forgetting. You'll see your reward go up, and then you keep training, and bam, it goes right back down, because I guess the working theory, maybe it's been demonstrated, but is that the model forgets the early parts of how to do the early balancing of the cart pull or whatever your environment is. And we often see, especially talking about DQNs, is that we see an overestimation of the Q value, because we see that, when you have your noisy estimates and you're taking the max of a noisy estimate, you're going to overestimate that expected value of the Q function, and that'll create a positive feedback loop. And you often see, surprisingly, there's been a number of interesting works here that even though DQN can be successful on like Atari environments, it's overestimating the reward by sometimes orders of magnitude. So it's saying, okay, it's getting a good score, but it's actually really bad at predicting what that score is. And we often, people didn't notice that necessarily all the time, because, hey, it's working. We look at the reward, over time curves, not necessarily the predicted reward. But basically that's also a common problem when it doesn't learn, is that it's overestimating Q values. So what I'm trying to say is that reducing epistemic uncertainty is not always as trivial as it seems. You can't just say, okay, I got more compute, I got another 100 hours of GPU time, let's just run it for another 100 hours of GPU time. That doesn't mean you're going to see any better results necessarily. So getting into it, the last thing I want to touch on is exploration and uncertainty. Exploration is a huge topic in RL, and a lot of it implicitly deals with uncertainty. So some of it also explicitly deals with uncertainty, and a few of those works are mentioned in the paper. Basically, we try to categorize works that explicitly deal with uncertainty only. Tons of works deal with it implicitly. So one way to think about exploration and uncertainty relationship is that if the model has high uncertainty, so if it's saying, if we assume the ideal scenario where training reduces uncertainty and sort of a direct one-to-one relationship there, which is obviously not true, as I just said, but assuming, operating under that assumption, we can see this relationship in the sense that if a model has high epistemic uncertainty in a certain collection of states, it means those states have simply not been trained on enough. And so you can reduce that epistemic uncertainty by going out and saying, I want to train and visit those states. And so what that often takes the form of, and so obviously the operating assumption is not true, but it's a helpful sort of guideline. And so what that often takes the form of is as some sort of bonus. So you estimate how many times you've seen these states or something. You estimate this epistemic uncertainty and then use that as a bonus for exploration, right? Because if you have low epistemic uncertainty, you don't need a bonus. You're already, certain in that area. And so you basically add that on to the reward. And so this is a super common technique in exploration, is using some sort of intrinsic reward. And so you'll see a lot of count-based methods, for example, where you approximate. Your goal is to basically approximate the number of times that a state has been visited, because the idea is that that correlates with this epistemic uncertainty. And you can see learned methods like random network distillation, where you have a fixed network that you feed the state through, and then another network that just tries to predict the output of that state or of that frozen network. And so the more right it's seen in the simple setup, the better it will get at fitting the network. Because in the more complex setup, right, and the more, if we're trying to do full RL, the training is non-trivial. But if you have a frozen network and a network you're just trying to match and just trying to learn the output of the frozen network, that's a lot easier of a problem. And so you can use the loss, where you're saying, okay, the difference, the error there between the frozen network's prediction and my learning model's prediction is the bonus, because as once you've seen the same state 1,000 times, you're going to be able to predict it pretty well. And so that idea is basically the same thing. It's conceptually very similar to the count-based method. It's just learning the counts rather than, counting them, I guess. And so this is, this is the key idea to a lot of exploration sort of ideas. And there's a lot here, I know. There's a ton of work in exploration that I have never, explored. It's so huge, but there's a lot of ideas here that I want to draw parallels to. So moving on, the two main techniques we're sort of talking about here are the bootstrapping or sort of ensembling approach. So you take a lot of networks or semi-independent. For example, if you bootstrap, you can use multiple heads of a neural network. So you share a convolutional, for example, for Atari, you would share a convolutional base and then use independent heads. So independent multi-layer perceptrons, basically, or dense layers that separate out. Very similar to how you would do in a model that predicts the state or predicts the policy and value. That's often has a shared base. Or you can make them fully independent, where you don't even have a shared base. You train them, and I say using varying degrees of separation, because you might say, okay, I'm going to train them completely independently, or I'm going to train them and randomly select them, or there's a lot of different setups that can exist here. And then you're going to run all of them forward on a given state. You're going to look at the differences in predictions. And you're going to say, that's my epistemic uncertainty. Because, if I've trained them to infinity, they're all going to, I guess, ideally, right? This, once again, not necessarily true for neural networks, but they're all going to ideally converge onto the same prediction. So my epistemic uncertainty is going to be 0. And so that's one common approach. Another common approach is called Monte Carlo dropout. So we all know what dropout is, right? For a neural network, you randomly set some nodes to 0, and it just works. It's one of those cool things to prevent overfitting. But the idea of Monte Carlo dropout, and I recommend you read the original paper that proposed it, to get more technical information into why this is actually the case. But if you keep the dropout layers in and then repeat many times, or you can just, depending on your implementation, you don't actually have to do forward passes, but you can tile the inputs. And using those different dropout instances, basically, where you go through and you differ which neurons you're setting to 0. You get those different predictions, and then you look at the variance as an estimate for epistemic uncertainty. And if you're interested in the math or reasoning why, I encourage you to read the original paper there. So both of those are great ways of estimating epistemic uncertainty. There are techniques, and you can adapt these techniques in certain ways for aleatoric uncertainty. There's also unique techniques. Obviously, there's many more techniques for epistemic uncertainty as well that I haven't addressed that I'll get to in the discussion. But aleatoric prediction as a whole is seemingly less common, but techniques do exist, so you can see those references there. So this is an overview of all the works that we covered in the original paper. I am not going to be going through all of these. I'm going to be going through 3 of them, 2 on the next slide, and 1 of them that I'm just going to talk about. And you can see a lot of different, pieces of information about them here. You can see soft actor critic is really common these days. But if you're looking for more detailed information, you can find basically a paragraph on each of these in the original paper. If you want more detailed information, you can of course read the original paper, which is always a great thing. So the first thing I'm going to talk about is I just picked these 2 sort of as these are not necessarily the best or my favorite or the best results or anything like that. These are just sort of, I think, represent important attributes that I want to talk about of uncertainty quantification. So basically the first one here, they take a very simple idea. They use an ensemble, EBQL, as you can see, ensemble-based Q-learning. So they have a bunch of Q networks that are, independent ensemble of them, and you can just run them forward, and train them. And I'll skip over the details of the specific, like how you pick them and at what times you do certain things. But if you actually see the original paper, you can see all the details. But what I'm trying to show here is on the right, you can see the a figure I took from the paper, which shows that this simple adaptation is competitive with Rainbow, which is sort of a DQ invariant that is the hodgepodge of everything. They took double DQ in, they took, prioritized experience replay, they took noisy networks, they took dueling networks, they took everything in there, right? They mushed it all together and they made Rainbow. That's like every combination of DQN, and it's still this simple idea, and Rainbow is very non-trivial to think about as an algorithm. There's a lot of different moving parts and it's non-trivial to implement, whereas this idea is very simple to implement and very simple to think about. So we can see it to help reduce the sort of algorithmic complexity, and this is one of the less explicit uncertainty awarenesses, but that's okay. Anyway, moving on to this other work, we have some results shown in the bottom right on Minotaur, which is just like a smaller version of Atari, and we can see that Minotaur, like Atari, is very Atari in its basic form is actually truly deterministic, but we add in things to make it not truly deterministic, but it's still, pretty deterministic as far as things go. We can see in this work that using only uncertainty awareness or uncertainty quantification in the action selection, so not using any fancy schmancy training routines, using it in the action selection can help improve things, even on on somewhat deterministic environments. Obviously, I guess it's stochastic because it's binary, but these are not like extremely random environments. These are very deterministic environments that we are forced to add noise to. The last one I want to talk about, and I'll go back a page, is Osband et al. 2018, which basically introduced the concept of a prior. So a frozen network that you do, your Q function is your Q function plus this frozen network. that is a function of the state. And so this has some nice properties that they talk about in the work. But the specific things I want to address there is that they introduce a lot of problems with some of the methods that we've talked about, specific or haven't talked about, more like, for example, count-based methods. They show have a number of very simple failure cases. Monte Carlo dropout-based methods have some interesting fail cases, and especially distributional distributed Q-learning or distributed RL, or distributional, I should say, where it's not distributed in the sense that you're using distributed computing. It's distributed in the sense that it's predicting a distribution over the Q values. For example, QR DQN, quantile regression DQN, or C51 is another one of this category. Those distributions often, people say, okay, well, they're mapping their distribution, so there's some uncertainty there, right? You can look at the variance of that distribution and look at and estimate some uncertainty, but the problem is that those are actually very poor models of the actual distribution, and that's something that work shows. It's a really great work. If you read none of these papers but one, I would encourage you to read Osband 2018, because it talks about a lot of stuff that goes on here. So anyway, moving on, we can see just a highlight of the empirical benefits. And this is all on the offline data set. The reason I just chose offline is because it's more standardized. Everyone uses data set for offline, or whatever D4RL stands for. Like, that's pretty standard, whereas everyone in online RL, some people do Atari, Minotaur, Mujoka, everyone does something different, so it's hard to compare across environments or algorithms. So we see here that on the left 3 columns, well, we have the environment names, and then we have behavioral cloning, which is sort of like the most basic thing, where you just try to learn and map exactly what the policy is doing. Conservative Q-learning, TD3, twin delayed deep deterministic policy, DDP policy gradient. It's been a while since I thought about all these acronyms. And BC, behavioral cloning. And then we see 5 works, which are all uncertainty aware, and we can see how they offer competitive or better performance than these sort of, I'm not claiming to know what the exact state of the art, it probably changes every single day, but these are very solid methods in offline RL, the CQL, conservative Q-learning, and TD3 plus BC. You'll notice a star on the rightmost column because those were only presented in graph form, so I'm sort of estimating those numbers. They're plus or minus 5 on them, I guess, would be the thing to consider. So moving on, the last thing I want to talk about, this is, I haven't gone into a ton of detail on what's actually in the paper, because if you want a ton of detail on what's actually in the paper, just go read the paper. But I'm trying to be giving a higher level overview. But the first thing I want to talk about is not actually the first thing here, but why not X? So why not some method of predicting uncertainty? Why didn't you talk about that? Why didn't you talk about safe RL or risk averse RL? Or why didn't you talk about as I said, more of these QRDQN, the learning the quantiles or the distributional RL, stuff like that? Why didn't you talk about that? And so I'm just going to give a blanket statement. Basically, in some cases, the distributional RL is because it's not really that useful for uncertainty, and it's vanilla context. But in general, it's simply because we focused on the biggest picture aspects. So Monte Carlo dropout and bootstrapping are in our impression, the most common techniques. And so, yes, there are other techniques. Yes, there are other techniques that might be better, but they're, we're trying to focus on the most common areas here. And regarding, all these other ways of doing things, all these other subfields of RL. There's simply a space limitation. There's, I believe, 7 pages plus 1 page of references or so. There's simply not enough room. And it's not the goal of the paper to be comprehensive. Obviously, you can target a journal and write 30 pages on this, but that's not the goal here. The goal isn't to be the, the encyclopedia entry for every single person who wants to know everything about uncertainty and reinforcement learning. It's sort of a motivating idea for those looking to make more robust and apply RL to their systems. It's sort of like, a pamphlet almost. I don't want to say it's a pamphlet, but it's just saying, hey, everyone who works with RL, here's a bunch of cool methods. You should try them out. You should read these papers. You should look at other papers. We took an assembly. There's tons more uncertainty RL papers, but here's a good examples and lots of, a diversity of works here. Check them out. And so that's really, why X wasn't covered. The other things I'll talk about now is, why is uncertainty quantification usually only done in the critic? Now, you wouldn't know this if you were just watching this video, but if you read the paper, this would be something that you would be asking. And because it only occurs in the paper, my answer is also in the paper. So if you're curious as to why uncertainty quantification generally only occurs in the critic, I refer you to the paper. But you would notice on the table that bootstrapping seems to be more common over Monte Carlo dropout. The exact reasoning, I don't have evidence for. Specifically, and this is, future work I'll talk about, but is bootstrapping fundamentally better at approximating over Monte Carlo at approximating epistemic uncertainty in reinforcement learning scenarios? I don't know, maybe, but I think the solution is that Monte Carlo dropout can be computationally expensive if you require forward passes or huge tiling, right? If you want to do 10 samples, you have to multiply your input size by 10, which is a lot bigger. Whereas with bootstrapping, if you're only caring about one head, then you can do techniques that can make it computationally efficient. So my guess is that there's a computationally efficient reason, and that's the main reason. But that's not a provable statement there. I am interested in the relative quality of the estimates of uncertainty for these two methods. And that is, for example, I'll just talk about the future work now. I think that is, how do we understand these methods, and how good are these methods? For example, if you plot, this is something I was doing, if you plot the predicted epistemic uncertainty using either of these methods over time, you'll see it very small at first because they're randomly initialized, and so all the predictions are, -1 to 1 or something, very small range, so the uncertainty is small. And you'll see it grow extremely rapidly and then fall back down. It almost exactly maps, when I was doing experiments, the paths that the mean squared error and the Q value predictions. For example, if you're doing a DQN, a bootstrap DQN, those functions, if you plot them like iteration versus, whatever the y-axis is, if you plot mean squared error, if you plot Q value, and if you plot epistemic uncertainty predicted, those graphs look very similar. And so it's interesting. Obviously, there's a lot more to be said there, but there's lots of future work there. Using new and all the great work, new methods, and all the great work that the community of traditional supervised deep learning uncertainty awareness has done, integrating the latest and greatest methods. There's lots of great work that can be done here. And last thing I'll talk about are what I think to be the most important takeaways, and that's just that uncertainty quantification, even if you don't use it in training at all, not even in action selection, can still be useful for your setup because you can know more information about what's going on in your system. I'm not saying that uncertainty is the key to explainable AI or something, but it is important it is an important tool in the toolbox for being able to understand certain fail cases and the brittleness and when and why that's going to happen. I think another important takeaway is that uncertainty awareness and quantification can help in a variety of circumstances, even when you might not think it would be that helpful. It can yield empirical results. It can also, as you'll see in some of the works, yield results much faster, reducing the total compute load or amount of wall clock time. There's lots of benefits. And the biggest takeaway I would say is that if you're trying to apply RL to a problem, try adding uncertainty quantification. And if you're interested in building more robust RL algorithms, as I am, then let's work with some uncertainty quantification and let's see what can be built there. And let's use these works that we've assembled and many more to see, what can be done here. And that's really the important takeaways. The goal here is to sort of expand the field, right? There's a lot more works, but it's really not that big, considering that the latest I saw was that there's like more than 50,000 deep RL papers being published a year. This makes up a very small section of that, but I think there's a lot of potential here, and I think that it's very underexplored, and I encourage everyone to explore it. And so these are the references that are numbered there. All of these are also referenced in the paper. If you're interested, there's also much more in the paper that I will, of course, link below. So once again, if you have any questions, feel free to put them down below or email me. But yeah, that's hopefully a high-level overview of the 2022 AIIDE paper, a review of Uncertainty for Deep Reinforcement Learning, written by myself, Owen Lockwood, and professor at Rensselaer Polytechnic Institute, May C. So if you made it this far, thanks for listening, and check out the paper.